Hi guys, so this is my submission for ENPM 808X for my final project, and it's called Spotless Mini Explorer. And just to give a brief overview about me is that my name is Sarthak Mahajan, and I'm currently pursuing my Masters of Engineering in Robotics at University of Maryland. And my areas of interest lie in computer vision, machine learning, and deep learning. Although my background is from electrical engineering, so coming from signal processing to computer vision is where I've grown over the years. I've worked at Omnipresent Robot Technologies, a startup in India, as a research engineer for almost 2 years, and we were making custom drones for industrial inspection. The motivation for this project is that seeing all the autonomous robots ever since the DARPA Grand Challenge in 2005 and the Urban Challenge in 2007, and we can see that the penetration of these robots in the real world has massively increased from like air or land or sea. And here we have like my personal favorites robots, and all these different robots motivate me to make systems more reliable, robust, and more prone and acceptable to the real life scenarios than just being test developments for different algorithms. And so this is the motivation behind the project. Giving a brief overview of the project is that I've created a package for ROS using Turtlebot, and what it does is it does autonomous navigation and mapping. And the way it does its autonomous navigation is by exploiting the frontier exploration algorithm. So I will get into its detail later on, but just for the overview, it also avoids obstacles. It relies on two very important packages from the ROS open source community, which are Gmapping and MoveBase. Gmapping is a package that helps you build a map of the surrounding, and MoveBase is a package that helps you move a turtle bar from your start position to a particular goal that you set. And for simulation and visualization, we've used Gazebo and Arviz. They're very important and useful tools, and very popular along with ROS. The simulator is Gazebo, and we use Arviz for visualization. So there are a lot of applications for such scenarios, such as industrial inspection, like what we used to do at my work previously, and creating a map of an unknown space, even search and rescue, surveillance, and another interesting aspect is like monitoring progress on construction sites and getting maps every now and then of the site. So coming to this project is the way I've designed the activity flow is that initially the Turtlebot does a full 360-degree scan, and it gets like a basic idea of what's happening around and in the environment. And the way it sees the environment is either it's occupied, it's empty, or it's unknown. And on the images on the left, the small dots is what it considers to be unknown, the darker dots is what it considers to be occupied, and the white space is where it considers to be an empty space. And the way it processes them is that it tries to understand which of these parts in the map are the unknown space. And those are basically our frontiers, and that's what we're going to explore. And looking again on the left, we can see that on the third image, we're trying to get the median from each frontier, which is like a center point for each frontier, because even though we know that we have to explore this particular part on the map, we still need a valid, a legitimate goal to provide to the Turtlebot in order to move in that direction. The images on the left are a pictorial representation, and then once we have these medians, we create like a point cloud or list or queue, in order to give this to the robot. And every loop we try to see if and not there are more frontiers in the point cloud. And usually what happens is that after a certain point, when the robot is done mapping the whole space, there wouldn't be any frontiers left, and that's when we would like to end. But till then, what we would do is that once we process the frontiers and get the medians, we would set the goal as the frontier which is nearest to the robot, and we would use MoveBase to move to that goal. And one interesting thing that MoveBase does is that it dynamically avoids obstacles. That's really helpful in this case. And once it reaches that position, it does the 360-degree scan, process the frontiers, and so on. And we keep moving until we've mapped the whole space. A very important aspect of the project is the system design for the class. So we have a base class that is Frontier Ops, and we have a derived class that is the Path Planner. Frontier Ops is the one that takes care of all operations related to the frontiers, and Path Planner is the one that takes care of getting the input of the map every so often and moving the robot to a particular goal that was provided by the Frontier Ops class. And yeah, so this is the rough structure. This is the exact structure of the class, and Frontier Ops is the base class, and Path Planner is the one that inherits from it. And how to build and run the project and the demo is what I'm going to show in the next video.